Welcome to the lecture on matter. So this lecture is designed for Biology 101, and let's take a look at the periodic table of elements first. I got to draw on this now. Woo! There's the periodic table of the elements. Probably important things to look at is elements are considered these sort of pure atoms of something, right? So let's go in and take a look at the middle piece here. This says that what's on here is going to have a symbol, which is a letter, that refers to the name of the element. So I'm going to go to the very first element in the chart, look at hydrogen. So that H in the middle right there is the one that explains what is the element. Right above it is the atomic number. So I'm just going to circle that over here. And then on the left-hand side, we can see the atomic number is 1 in hydrogen. And this is actually the number of protons. I'll define all these in a minute. The mass at the bottom is the, sort of, you can think of that as the weight if you want. And it's actually the number of protons plus neutrons. So I'm not a chemist, but some of these things are kind of important for basic biological concepts. So let's go back and take a look at what we're talking about when we talk about the atomic structure. Atomic structure. Basically, in an atom, there's an area in the middle that is the nucleus, just like we have for a cell, and that's where you find protons and neutrons. Now, neutrons and protons are each weighing 1 Dalton each. 1 Dalton. They weigh the same. The difference is the protons have a positive charge and neutrons have no charge. So neutrons are just added weight or mass, if you want to think about it that way. But protons actually add a charge. So if you take something like hydrogen, which we just looked at up here, you can see that hydrogen has an atomic number of 1, which is 1 proton. So I can put the 1 positive proton in the middle. I could draw it like this if I want. And then it's going to have electrons. Now I haven't mentioned electrons, but electrons are negative charged. And they're very small. Basically, they have no mass. So almost no mass. And they sort of fly around the outside. And here's where I get a little weird about it. I'm going to draw them about as large as the proton. They're really much smaller. And you can think about them as whipping around here at the speed of light around this nucleus, right? They're just going, and it's not really a circle that they travel in, I've been told by the chemists, but they're going so fast it's hard to tell where they are at any given time. The important thing is that in their sort of natural state in which we draw them, the number of protons should equal the number of electrons. Now that can change in nature, so this can change, and if that changes, that results in a charged particle. Okay, a charged particle, if that changes. For example, if an atom loses an electron or it gains a proton or something, it changes the charge. So whatever you have more of, that's the way that you're charged. Okay. Now let's go back to our periodic table of the elements and take a look at which of these elements are going to be really important for us. Let's look around. We're going to be really interested in sodium, potassium, that's pretty important. Nitrogen's important. Carbon is super important. Oxygen's super important. There's a few others that we'll deal with today. We're gonna be looking today at chlorine, and most of the ones that are important for humans are above this line here. Okay, like in biological life. The other ones are kind of important, but these at the top make up much more of the of living organisms. and they make a lot of carbon bonds, so that's why we call it carbon-based life, Scotty. At any rate, let's take a look then at one more important aspect of the atom, and that is the way those electrons are set up. So let's take a look at something like oxygen. Okay, I'm going to draw oxygen now. So to draw oxygen, I look it up and I see that it has atomic number of 8 and it has a weight of 16. So that means it's got to have 8 protons. And I should mention this, and it has 8 neutrons. What I should mention here is that you see that atomic number in each of these is really important because the atomic number actually determines what element it is. So every unique atomic number has a unique element associated with it. So that's like the super deterministic number. Sometimes individual atoms can vary in the number of neutrons that they have, and those are called isotopes. They weigh different amounts, but they have the same number of protons. So they're still the same element, which is fine and good. And the number of electrons and the number of protons is always balanced, right? The same, unless, of course, an electron has been lost or gained for some reason, which we're going to talk about in a minute. But pretty much the number of protons doesn't change, because if you were able to change the number of protons, you would be changing the element. And so, for example, if you took a proton from fluorine and you left, it would change into oxygen. And that's really hard to do, like nuclear bomb, hard to do. So really complicated. So the number of protons pretty much stays the same. Now, the way those protons are, so for oxygen, I'll draw oxygen's little model down here, and it's going to have 8, 2, 3, 4, 5, 6, 7, 8. And I might as well put these as all pluses, right? And it's going to have 1, 2, 3, 4, 5, 6, 7, 8 zeros, which I'm going to call neutrons. So these are the neutrons, and these are the protons. Now, when I count electrons, I'm going to have to move my word oxygen because it's in the way, first of all. We'll put it over here. When we draw the electrons, I have to put 16, did I say that? Not 16 electrons, but 8 electrons. And electrons are found in 2 shells, or, well, I shouldn't say 2 shells. There's more than 2. In this case, there's only 2. In the first shell, you can have 2 electrons, and then it's full. All right? And then you have to move to the next shell. The next shell has up to 8 electrons. 8 electrons in second shell. And you can have up to 2 electrons in the first shell. And what that means is that I can draw them in here like this: 1, 2, 3, 4, 5, and 6. I like to draw them in pairs if I can, and there's only 6. Now, each atoms are sort of stable with regard to the number of electrons when the outer shell is full. So if they only have one shell, then either they have a number of 2. If they have 2 shells, second shell gets 8, and the third shell gets 8. Now, this is a dramatic sort of simplification, but the idea is that atoms will try to collect electrons until their outer shell is full. And so sometimes that's done by getting rid of one, or sometimes it's done by gathering up one or sharing one with another atom. And we'll talk about in the next lecture how that happens. So there you go.